Today, we continue our series on collision detection by explaining how to implement the collision of a bounding sphere and a plane, and then a bounding sphere and a polygon. A bounding sphere is defined by a radius, which determines its size, and a position, which determines its location in space. A plane represents a two-dimensional surface of infinite extent. It is defined by a position, which represents a point on the plane, a normal vector, which defines its orientation, and a shift constant, which indicates the signed distance of the point on the plane from the origin of the world. The signed distance can be negative or positive, depending on its proximity to the world origin and whether the surface normal is pointing away or towards the world origin. The plane shift constant is calculated using the dot product of the point on the plane and the plane's surface normal. The plane equation has the form a times x, add b times y, add c times z, minus d equals 0. Vector components a, b, and c define the surface normal, whilst x, y, and z represent a point that lies on the plane. D represents the plane shift constant. The part of this equation before the subtraction operator is a dot product between the plane's normal vector and a point in space. When this dot product equals the shift constant, the point lies on the plane. The sphere with plane static function is simple. We perform a dot product between the sphere's position and the plane's normal to get the distance of the sphere along the normal. This value could be positive or negative. We subtract the plane shift constant from this value to get the distance from the plane surface to the center of the sphere. We convert this potentially negative value to positive using the Fab's f function, then check if it is less or equal to the sphere's radius. If so, there is collision. A polytope is a general term for a geometric entity with flat sides in any number of dimensions more than 0. In 0 dimensions, it is a point. In 1 dimension, it is a line with two vertices at either end. In 2 dimensions, it could possibly be a triangle, square, or an arbitrarily shaped polygon. A polytope of 3 dimensions is also called a polyhedron, examples of which are pyramids, cubes, and 3D models. Polytope 2s, aka polygons, are good for modeling character viewing frustrums in top-down games and handling collision detection of arbitrarily shaped entities, such as buildings and furniture. For our purposes, polygons are assumed to be convex. A convex polygon has no internal angles that exceed 180 degrees. Convex polygons also allow a line to be drawn between any two points within it, without intersecting an edge. The sphere-polytope static function makes a few more assumptions. First, that the polygon's vertices have distinct positions. If not, the edge collision tests will not work. Secondly, it assumes the polygon's vertices follow an anti-clockwise winding order. This is pertinent when we're checking whether the center of the sphere is within the polygon. Thirdly, that the polygon has at least 3 points. Otherwise, it should just be a line segment in sphere test or a point in polygon test. Finally, it assumes both the sphere and the polygon are at 0 on the z-axis, and the polygon lies entirely on the xy plane. This is a specific rather than general solution, which would account for the polygon being arbitrarily oriented. We first ensure that the sphere is close enough to 0 on the z-axis. Instead of comparing the sphere's z position to exactly 0, we use an epsilon check, a small tolerance value to account for floating point inaccuracy. In this case, we use 1e-4, which is 0.0001 in decimal. Floating point values often contain small inaccuracies due to how they're stored in memory after calculations are settled. We start by checking whether any of the polygon's vertices are inside the sphere. For each vertex, we compute a vector from the sphere's center to the vertex and then compare the dot product of the distance to the squared radius. The dot product of the distance with itself is tantamount to self-multiplication and makes it proportional to the radius squared and allows us to avoid the costly square root calculation needed to calculate the vector magnitude. This test quickly catches some collision cases but misses others, like when an edge intersects the sphere without any vertex being inside. Next, we check whether any of the polygon's edges intersect the sphere. A polygon with n vertices has n edges. Each edge connects a point to the adjacent one, wrapping around at the end. We use a modified version of the ray-sphere intersection function covered in a previous tutorial, now constrained to a line segment. Please refer to it if you would like an in-depth explanation. The key difference is we check whether the intersection point lies within the line segment bounds. If it does, there is a collision. However, this test still misses cases, like when the entire sphere lies inside the polygon. The Point-in-polygon function handles this. This function checks whether the central position of the sphere is within the polygon. A binary search progressively searches a smaller subsection of a data structure to find a value. This smaller section is half the size of the previous and encompasses either the left or right-hand segment of the previous section. The do-while loop performs a binary search over the polygon by creating a triangle using the first vertex, the currently set mid-vertex, and the point we are testing to see is in the polygon. The isTriangle counterclockwise function is checking if the point is on the left or right-hand side of the line formed by the first vertex and currently set mid-vertex. If the point is on the right, the function will return true and increase the low value. If not, it will return false and decrease the high value, effectively halving the search space upon each iteration. The isTriangle counterclockwise calculates the cross product of the two vectors formed by point 2 and 3 subtracted from point 1. The cross product is the vector that is orthogonal to both input vectors, which means it is offset 90 degrees. We perform a dot product with the cross product result and a vector pointing towards the viewer. If it is more than 0, it means the winding of the triangle is counterclockwise. If it is less than 0, then the winding is clockwise. If it is exactly 0, it means all the points are collinear. Back in the function, we now check if the low value is still 0 or the right is still set to the number of polygon points as they were originally. If so, the point cannot be within the polygon because both would have been updated at least once in the do-while loop above. In the final section, we check whether the sphere's position is to the left of the line formed by the low and high vertices that were chosen previously. If so, it is within the polygon. However, if the polygon was defined with clockwise winding and the sphere's central point was within it, this function would lead to a false negative. And with those tests, vertex proximity, edge intersection, and point-in-polygon, we now have a robust solution for detecting static collision between a sphere and a convex polygon. Thanks for watching, and as always, stay curious.